Welcome back, folks. Still working with Thevenin's theorem. This is kind of the payoff. It's a bigger circuit. It's got multiple, we're going to break it into multiple subcircuits. And this is kind of what makes Thevenin's and then Norton's by extension some of the most important theorems that we work with because it allows us to reduce complexity. We take the subsystems, we build individual Thevenin equivalents for them, and then we figure out what's going on in between the circuits. We might do this with microcontrollers or wall outlets, all of the examples we talked about before. We're interested in the voltage between the things we're connecting and the current being passed between the things we're connecting. So this is still an academic example, but I think it's big enough to demonstrate the point, but not big enough that we get lost in the details. So let's check it out. And there's the circuit. We're going to break it into two subcircuits. Completely made up, by the way. Completely made up. But we're going to take this, and maybe you think of that as the microcontroller, and then this is the circuit that you build to connect to that microcontroller. Well, what's the voltage here? So what's the microcontroller going to read? And then how much current is required to drive your circuit? You got to think about that when you're designing. So we're going to take what's in the yellow box, and we're going to find the Thevenin equivalent for it. It's a voltage supply with a series resistance. And then we're going to take what's in the, I'm going to call that light blue. I'm really bad with colors. We're going to take what's in the light blue box, and we're going to find a Thevenin equivalent. Now, it's drawn headed to the left, right? But it's still a voltage supply with a series resistance. So it's still a Thevenin equivalent. And we're going to get into more of that when we talk about source conversions. But you may not have seen it that way. You may go, well, it's supposed to go to the right. Doesn't matter. It's still in series. It's still a Thevenin equivalent. Okay, so let's do this. Let's find the Thevenin equivalent, and we've got to fill in the voltage and the resistance, and over here we got to fill in the voltage and the resistance. So in order to do that, I'm going to steal this chunk of the circuit, okay, and figure out what's going on. Okay, so we've got the yellow boxed circuit over here, and we've got to find V open circuit for starters, and then we can go find our Thevenin as well. All right, so we've got one mesh, but then we've got to write a KVL, and that one mesh we write a KCL for it. Okay, so writing our KCL for the one mesh, we can say that I is equal to negative 2.2 amps. So that's simple enough. If we're being good engineers and we mark out our polarity to look like that, then we can find that voltage by taking I, I'll do it in orange, sure, and multiplying it by 10 ohms. Okay, I is negative 2.2, so this voltage is going to be negative 22 volts. Okay, so we get negative 22 volts there. So I've got some sign things that are going to be a little goofy, but we'll survive if we follow along carefully. Okay, writing the KVL around here, up to there, we say we drop, but we drop a negative 22 volts. Okay, over here we know it's 0, right? That's 0 volts because there's no mesh. So I'll say that we drop 0 volts. We could rise 0 volts, but really doesn't matter. Next we drop across VOC, and now we drop across the 32 volt, and we're back to where we started, so that's equal to 0. Okay, not so straightforward. It's funny when you start ripping components out and strange things happen. Okay, so I got to get VOC over to the other side, and I'm going to have 22 volts and negative 32 volts. Okay, so I want to flip-flop those sides, so I can say VOC, and this is going to end up being negative 10 volts. Okay, and that's our result. So negative 10 volts. It's pretty good. We can come back up here and we can say that this is negative 10 volts. Okay, and we found that from the analysis below. Next step is to find the Thevenin resistance here. So let's do that right next to it. I'm going to grab another copy of the circuit. You end up redrawing a lot of circuits in these sections. And I'm going to use the first method. I'm going to use the first method because it's the quickest and it's the easiest in this case. You can use any method you want on this one. There's no dependent supplies and there are independent supplies. So any of the three methods that I've introduced for finding our Thevenin would be fine. In looking at this, the first one's going to be the fastest. I take each independent supply and I replace it with its ideal resistance. Right? So that's an open. So that just disappears. And that makes this easy. Okay, I take the voltage supply. Since this one's a voltage supply, it gets replaced by a short. And then we find our Thevenin between these terminals. Okay, anything in series, anything in parallel that we can combine. If these two are in series, they share this node exclusively. So our Thevenin equals 10 plus 18, or 28 ohms. I almost said volts. It's ohms. Okay, so we can come back up here. I suppose I should be color consistent and say that this is 28 ohms. Whew. Okay, so now we got to do the same thing, but we're going to do the same thing for the blue circuit. Trying to move through these as quick as possible, but it's also good practice for you to see these. Okay, so we find this one, whole separate Thevenin equivalent, right? So I'm going to give myself a dotted line just to make sure I'm careful. Okay, we need to find V open circuit. Ooh, a little more complicated. It's got two meshes. Okay, I1, I2, and we have a super loop, not the end of the world, but we can write our KVL for the super loop, and we got to write a KCL. I think I meant to write KCL first. Okay, does I1 touch the current supply? Yes, and it goes in the opposite direction. Does I2 touch the current supply? Yes, and it goes in the same direction, and that's all equal to 2.5 amps. So there's one equation for my system. Pretty quick. Okay. The super loop goes around here. Bink, bink, bink. Okay, we're gonna, what does I1 share with the super, well, it is the super loop. What does I1 share with the super loop? And it shares 9, so it's going to be positive because it's I1 is part of the super loop. What does I2 share with the super loop? It shares 18, and again it's positive because it's part of the super loop. And then looking for any sources, it looks like we drop across the 36 as we move counterclockwise. Okay, and there's our second equation. Okay, solving that, I think I can do this one pretty quickly. I think I can do it correctly. 9, 18, negative 36. Oops. I1 equals negative 3 amps. I2 equals negative 500 milliamps. Okay. So now we got to find V open circuit, and we're kind of forced to use the polarity that I drew up there. Whoops. And it opposes I1, right? Passive sign convention tells me that the positive current direction is going to be down. I1 touches it, but goes in the opposite direction. So just be very aware of that negative sign. Let's see, V open circuit, is that still on the screen? Yep. Is going to be negative I1 times 9 ohms. So negative I1 is actually 3. So it's going to be V open circuit equals positive 3 amps times 9 ohms, also known as 27 volts. Woo! Okay, let's get that labeled on our circuit up here. So this is 27 volts. We'll stick with white on this side. Who knows why? Okay, now we need our Thevenin for the light blue side of the circuit. And I'm going to use method 1 again. Again, it's going to be the quickest and easiest. I replace the independent sources with their ideal resistances. So that one gets opened up because it's a current supply. This one gets shorted because it's a voltage supply. Draw that short. Okay, and we find our Thevenin between these two terminals because that's where the load on this circuit's going to be. Okay, these two are then in parallel. They share this node and they share this node. So our Thevenin is going to be 9 in parallel with 18. Feels like that should work out to something nice, but rather than risking doing horrible mental math, yeah, works out to something nice. It's 6. Okay, so that ends up being 6 ohms. Okay, so now we have much less analysis to do down here. Hopefully we end up with the same value. Let's do the analysis on the Thevenin equivalents, and then I'll go back and I'll write out the analysis. Maybe we'll do a magic snap to make that analysis happen much faster. But I'm going to steal this circuit and bring it down here. How much room do I have left? We're totally doing a magic snap later. Okay. Where I make answers appear magically. Okay, so the analysis on this, well, there's only one mesh, right? So we're going to find I out pretty easily. There's this mesh here, and I'll call that I. There are no current supplies, so it's going to be 1 kVL. So we're going to write that kVL. We're going to go up a negative 10 volts, just to mess with your head, right? So plus negative 10 volts, watch your polarities, minus 28I, minus 6I, and then minus 27. And we're back to where we started, so that's equal to 0. Okay, that was using the passive sign convention with those polarities. I go up, I go down, I go down, I go down, right? So up, down, 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 and then we plug in whatever values we need to. Solving this for I, let's see, so this becomes negative 37, but if I move it over, it becomes positive 37. And then leaving these right where they are, I get negative 34I. Okay, so I is equal to 37 over negative 34. A little more than 1, a little more than negative 1, I should say. 37 divided by negative 34 is equal to negative 1.088. And that's in amps. Okay. If we have that current, I'm going to store it so I can use it easily in my calculator. Then we need to find V out. Okay, and we find V out by writing another KVL. So it looks like they're all about equal. I'm actually going to write this one because there's less goofiness with the signs over here. So I'm going to write my KVL around this way. Okay, so I'm going to go up V out, I'm going to drop across 6I, I'm going to drop across 27. Can I get that all on the screen? I'll do it in green so that it lines up with what I'm doing up there. So V out minus 6I minus 27 equals 0. Okay, that's the KVL to find V out. Ooh, I ran out of paper. Let's make it happen. I'm all the way down at the bottom here. There's a limit to how many pixels I can have. I want more. So we're gonna need a second sheet of paper. Yeah, you're quoted. All right, so V out is equal to positive 6 as I move that over to the right hand side times negative 1.088 plus 27, and that's going to be equal to 6 times the current I found plus 27, and we get 20.47 volts. Okay, so I've got a current and I've got a voltage. So let's mark that up here. So V out is 20.47 and I out is 1.088 amps. Okay. Abusing my microcontroller example, that would be the voltage that might be read by an analog to digital converter, although that's a very high voltage for a microcontroller. And this would be the current that the microcontroller would need to supply to the load circuit in order to get a good reading, have it function properly, something along those lines. Again, that's a really high current, so maybe not a perfect example, but those are two numbers that are of interest. Now, the company's not going to give you all of the details of the microcontroller, so you might get this information if you're lucky, and you might be able to find this information from your own circuit if you need to. Maybe it's a sensor, it's a prepackaged sensor, and you don't have that schematic. Maybe all you get is something equivalent to the Thevenin and voltage and resistance. Now, all of that should match what we see here. So I'm going to pause the video. I'm going to grab all of this and move on to a second image. So you're going to get two images. You've probably already figured that out. And we're going to reanalyze this, and we should end up with the same result. And that's the power of Thevenin. We can talk about the equivalent circuits without having to know all the details and end up at the same result. So let's go ahead and copy this and see on the flip side. Holy cow, look at that thing. Well, wouldn't you rather use the Thevenin equivalent circuits than going through this mess? This isn't even a particularly... It got sloppy. It got a little sloppy. I think we're going to be okay. I use the shortcut. There's 4 meshes. Don't get confused by the dotted lines. Those are just to kind of block off regions of the circuit. So there's 4 meshes. I1, I2 is around here, I3, and I4. There's 2 super loops. I said it can happen. Here it is. And so I wrote a KCL. This is the KCL for I1 and I2. This is the KVL for I1 and I2. Here's the KCL for I3 and I4. And the KVL for I3 and I4. So going through all of that mess, very grateful that I could just throw the shortcut at it. I found I1, I2, I3, and I4. Now, I out, maybe I didn't explicitly say this here. Come on, I out. Does I1 touch it? Nope. Does I2 touch it? Yep. So I out is really just whatever I2 is. Okay, I3 doesn't touch it, I4 doesn't touch it. So I out is negative 1.088 amps. And that's what we found from the Thevenin equivalents. Man, it would be much easier to just use the Thevenin equivalents. I wouldn't have to do all of these shenanigans. Okay, once I found I out and I realized it was the same, I went, okay, I feel like I did the analysis right at least. But I still needed to find V out. So I followed the yellow path for V out because it included V out and it only forced me to use Ohm's law once. I could have gone over here and avoided the current supply, but I would have had to do Ohm's law twice. I am lazy. So I went up V out, down 18 I4, since the polarity is marked that way, and then down 36, and I'm back to where I started since this is all one big node down here. And then I just solved for V out. I plugged in I4, and hopefully I know we got the right answer. So here's up V out, down 18I4, down 36 equals 0. Rearrange it to solve for V out, plug in the value, and we end up with 20.47. Okay, now this all matched. Let's see, we've got negative 1.088 amps. And that's what, here's a copy from the previous image. That's what we got for the current flowing between the two subcircuits. And we got a voltage of 20.47, and that's what we got from for the voltage that exists between the two terminals on both of the subcircuits. Okay, I would much rather do this analysis, and you're more likely to get that information from the company. And this is why I say Thevenin is arguably the most important theorem that we study. It allows us to take complexity and reduce it down and do much simpler analysis, but still get the right answer. And that's what we're after. Okay, hopefully you're a believer of Thevenin. I mean, everybody loves a good French telegraph operator, don't they? He liked to play the viola. He lived alone. He helped raise his niece. He was, you know, by all accounts, was a decent fella. Anyhow, we got to do some other stuff. We got to look at Norton's. Okay, Norton was is equally important. How do we do equivalent circuits with current supplies? We also have to look at something called maximum power transfer theorem. So I think that's where I'm gonna snap the line. We did Thevenin's. We're good. Norton's is going to be a lot quicker because you're good at Thevenin's now. You're really good at it. So we're going to snap the line here. The next set of lectures, we're going to take care of Norton's and maximum power transfer. I believe in you. Okay, so stay tuned and good luck, folks.